Okay, here we are, section 16.5 from the book. This has to deal with surfaces and surface area. So we're going to start with some recollections here. For example, we've already shown how to parametrize a curve, C, and its R sub t is f of I plus g of j plus h of k, where f, g, and k, or f, g, and h are functions of t, and t lies in some parametric interval. And we also have just regular old functions, y equals f of x or x equals f of y. Okay. We've also parametrized other things like line segments and stuff like that. But basically there's two ways here. There's an implicit way and an explicit way. One involves parametrization and the other is just explicit functions. Now to define a surface, we take a vector with two parameters, u and v, and we just apply what we know like this, okay? And u has to have some interval and v has to have some interval. So u goes from a to b and v goes from c to d. So we're just now doing something super cool, and this defines a surface. So this parametrization defines a surface. Now, a couple of you are in my linear algebra class, and really, if you think about it, parametrization, it's just, well, here, since we have a recollection here, recall. So we have this curve. I'm just going to work in two space because it's easier to draw a picture. So R sub t is S sub t I plus g of t j, and t runs from a to b. So as t runs through a to b, R takes these values and plots it in what? Plots it in the xy plane, right? So over here is where the curve is going to be, and over here I'm just going to have the real number line, and from somewhere along here, a to b, I have my t runs in here, okay? And so let's say the curve C look like this, right? Well, what's really happened here is when you input A from here, it gives you R of A, and each point along here, I'm doing discrete here, so each point along here gives you points along the curve, and the last one here does this. So this is what we call a mapping. Okay, we've mapped this line segment here in R1 to this curve in R2. And I think just Jack and Andrew are in linear algebra with me. This is a linear transformation from R1 to R2. And you can find a matrix with the ft and the g sub t that sends it from there to there. So a little aside for those guys. Okay, so let's look at now what we're doing here. We're making surfaces. Keep that picture in your head. So remember, we have, go away, u, we have u and v, right? So u runs from a to b, and oops, it's not a vector, surprisingly. and V runs from C to D. And instead of having a parametric interval, we have a parametric region. Okay, and the region is in the UV plane over here, and this is a parametric plane. Here's U, and here's V, right? And U goes from A to B, and V goes from C to D. Let me get some pretty colors in here. I'm going to make this blue. Okay, so if you look at this rectangle, this is the parametric region. All of this, all the points in here and on the boundaries. Okay, and then over here, I'm just going to stick with quadrant 1 here, just because it's cleaner. There's X and there's, oops, I forgot I'm doing the 3-space example. Okay, this will be better. So now we have over here in X, Y, Z, right? So over here we're in R2, over here we're in R3, and I'm going to draw a surface, and my surface is going to look like it's going to be purple, or at least the outline is. And so let's say the surface, this is my surface S. And just like before, all we've taken now are ordered pairs, so let's pretend that this corner here, which is the point, what, BC, this guy maps to that corner, let's say, and this one maps to this corner, and this one maps to this corner, and this one maps to this corner, and all the points inside here map to this surface. Right? So now we have this mapping from R2 onto R3, and as we run through this domain, our parametrization gives us this smooth curve. Okay. All right, so that's sort of the, well, that is the picture of how these parametrizations work in the going from UV to XYZ. All right. So let's look at an example here. We're going to let Z be the square root of x squared plus y squared, and Z is going to run from 0 to 1. This gives us a cone. We've seen this before when we were doing triple integrals and doubles, right? And let's parametrize the surface. Okay. Well, what are U and V going to be? The obvious candidates are R and theta, right? Because we're on a cone, which is like a cylinder, so we should use cylindrical coordinates. So we're going to let U be R. Actually, that's not how I want to do this. Hold on here. What I'm going to do is I'm going to let X be R cos theta, Y is R sine theta, and Z turns out to be R. Okay, so the parametrization, so yeah, R is U and theta is V, is well, what is it? It's R cos theta I plus R sine theta J plus RK. And what does R do? R runs from 0 to 1, and theta runs from 0 to 2 pi. Okay. All right, and that gives us the surface of the cone. With height 1 and on the unit circle down here. Okay. You can also do this with spherical coordinates as long as rho is fixed. It works. Okay, so what we want to do is figure out how to find surface areas. And from a teaching perspective, I love this because it's just more of the same. You make a shape on the surface that has a partial or a derivative to it, or a differential, I mean to say. You make the Riemann sum to add all of them up, and then you turn it into an integral, and it's all good. And so this is one of my favorite pictures. I've been practicing this all morning to try and give you the right sort of concept of this thing here. And as I sit here, I already want to change it. So, all right, let's do this. I need a fresh screen here. Okay. So we start with a surface here. I'm gonna get it way up high here. Okay, just like before, there's Y, there's X, and there's Z. Okay, I kind of liked the blue before, so I'm going to make. If you get the curve to be a special way, the picture comes out really nice. That's what I'm trying to do here. So this is just, it's a random curve. Surface, I should say. I'll call it S, not a curve. So this blue is a random surface, and it has some parametrization. So over here, I'm going to put my parametric domain in the UV plane. Just like before, we're going to go from A to B and from C to D. Okay? And so we get this. Sweet! I knew that would work. So this is the little, this is our little region, well, R. We'll call this thing R, right? Parametric region. And all the points from this region here mapped over to this chunk of surface area here. Okay. And the idea is we want to find the area of this surface piece here. Okay. So let me clean this up, because this is going to get really messy. Okay, if you go back to Calc 2 and you think about on these intervals, what did we do? We broke this up into n subintervals. Each one had an area, and we found the area and the height of the function and all that. This is a little different than that. What we're going to do is we're going to take just a little patch here, a little rectangular patch, right? And these are going to have sides, of course. And we're going to map this patch to some little patch over here, okay? And the orientation is important. So if you take this point down here in the corner, I'm going to map it to right here. Okay. And then if you take this point up here, we're going to call this P naught. And it's going to come up here. Right, there's P naught. Okay. And then if you take the other two corners, they're gonna make a little patch here. on the surface, right? And this is actually curved, so following the curve of the thing. So it's not a rectangle or a parallelogram or anything. It's a swath of cloth on a surface that's smooth, okay? All right, so here's what you do. You take a, we'll call this C1. This curve is C1, and this curve is C2. And they intersect at P0. And they're on the surface, and they are little curves. They're not straight. It looks straight in the picture, but they're not. Okay. So what we do is we take a partial vector r sub u, tangent to C1 at P0, and we take a partial vector with respect to V, tangent to C2 at P0, okay? So this is what it looks like. R of u goes like this, and R of V, come on, R of V goes like this, and they intersect at P0. Okay, so the little distance from here to here is delta U, and the little distance from here to here is delta V. If you remember Calc 2 and all those constructions, I think you see where this is going. Okay, and what we do is, and this is the super cool part, if you take the vector r sub u and multiply it by this little differential of u, you get, I need another color. I told you this was going to get messy, but it's all right. We'll clean it up. What you get is you get a little chunk here that lies over this curve C1. And I'll make a bigger picture in a second. And you do the same thing for V, and you take the vector r of V and multiply it by delta V, and you get just a little chunk here. In fact, it overlaps. And so I'm going to take this chunk out and make it super magnified. So what you have is you have a parallelogram here. This is r sub u delta u, and this is r sub v delta v, and this is the point P0. And underneath it is the curve, and the curve is sort of projected underneath it here. And so here's the curve slipping away from this perfect parallelogram, but because we're so small at this point, this little height here is negligible. And so this little parallelogram, which looks like this, this is so much easier to do in class. I normally have volunteers hold things and pieces of paper, and it's super fun, but I'm doing the best I can here. All right. So this little parallelogram looks more like a rectangle. It has what length? Delta u r sub u, and then width delta v r sub v here. Okay. And this parallelogram is approximately the area of the swath, right? And when I say the swath, I mean this little piece of curve here, and the parallelogram lies over it, but they're so close that for all intents and purposes, their surface areas are equal. Okay. So, we learned early on that when you have two vectors that are in the same plane, because these are both in the plane perpendicular to the point P0 of the surface, the area of the parallelogram is equal to what? It's equal to r sub u delta u cross product r sub v delta v. It's the magnitude of this cross product vector. And that's a result from physics. It's also from our class. We did it 13 weeks ago in chapter 12, I believe. Okay. So now we have the area for one of these little guys. Of course, what do? We set up the nth partial sum. K goes from 1 down to n. R sub u cross R sub v delta u delta v. And this is actually a double sum, but I'm not going to write it like that. And you let the limit as n goes to infinity of Sn, assuming it exists, but of course it does. And you get the integral what? You get the integral of r sub u cross r sub v du dv. And u goes from a to b. And v goes from c to d. And now this whole piece here is what we call d sub sigma. It's the surface area differential. Right, and there it is. I mean, that's how you find the surface area of a parametrized surface. Okay. All right, so let's go back to our cone. Let's go back to our cone example. Let me go back to black here. We have z equals square root of x squared plus y squared. Where did it go, Pullman? I know it is here. I just did it a minute ago. But z goes from 0 to 1. There we go. So the parametrization was r of r theta is r cos theta I plus r sine theta j plus rk. Bam, bam, bam. And r goes from 0 to 1. And theta goes from 0 to 2 pi. Okay. So step 1 is to compute. So we're finding the surface area. Just applying the last thing. So the step 1 is compute r sub r cross r sub theta. Now these are partials. Okay. And using the matrix form, we have I, J, K. Okay, so the r partial of x is cosine theta. The r partial of y is sine theta. And the r partial of z is 1. Okay. The theta partial of x is minus r sine theta. The theta partial of y is r cos theta. And the theta partial of z is 0. And this becomes k times what? Cosine theta sine theta minus r sine theta r cos theta minus 1 times ij minus r sine theta, r cos theta, which becomes r cosine squared theta plus r sine squared theta k minus r cos theta I Why am I struggling with this? I hate doing these things. R cos theta I plus R sine theta J. Okay. All right. So this becomes what? RK, because the cosine squared plus sine squared equals 1. RK minus R sine theta J minus R cos theta I. Sorry for the ordering. Okay, now we want to find the length of this vector, and it's the square root of r squared plus r squared sine squared theta plus r squared cosine squared theta, which is r squared plus r squared sine squared theta plus cosine squared theta, and that's the square root of 2r squared, which is r square root of 2. There we go. Okay. All right, so the surface area turns out to be, the integral of theta goes from 0 to 2 pi. R goes from 0 to 1. Root 2 r dr d theta. And this becomes, well, you got to do it, I guess. So root 2 over 2 r squared from 0 to 1 d theta, which is root 2 over 2 root 2 pi square units. Alrighty then, that was super fun. And there was some review in there from last stuff we've done in the course, so that's good for final study in here. So also, if you have an explicit form, say f of xy equals c or something for the surface, there is a formula for computing the surface area of that, which is it's del f over so the norm of del f over the norm of del f dotted with p dA, and here p is either I, j, or k. It's usually k, but it doesn't matter, right? And maybe when we meet, I'll do an example of this guy. This should be also a Z in here. But I'm not going to go through how you get this. It's just you parameterize this thing, and then you come up with the del F and the del F.P. It's pretty straightforward. So that's that. And I forgot to assign homework. So this is homework 14. It's not collected. It'd be crazy not to do it, though. Just had it written down. The problem with getting organized is that it completely unorganizes you. Just had it written down here so I could pump it out. There it is, 16. Okay, so 16.4 was Green's theorem. 4, 6, 9, 16, 19, and 23. 16.5, 4, 19. I'm going to put 17 to 26, your choice. And then 48 and 49. This is Thursday. I'll have another video tomorrow. I'm not sure if I'm going to do 16.6 or not, because I want to do 16.7. Definitely doing 16.7, but 16.6 is sort of, no, I'm not a big fan of it, but I think you need part of it for 16.7. So when I figure out how the video for 16.7 looks, there might be a piece of 16.6 that I need, and I'll just use it and say, okay, this is the only thing I needed from that section. Just slash and burn. But yeah, that's a lot of work. So stick with it. Ask lots of questions. Come to office hours. And you know, I think our last section will be 16.7 or 16.8. So we're at the what? Bottom of the ninth? No, top of the ninth inning. All right. See you in a minute.